Uh, yeah. Hey all. Let's solve today's daily lead code. It says count the number of complete components. I'm a bit late today. It's around 11 p.m. So let's see how we can approach this problem. Let me see when's the last time. It's March 2025. Let's go. It's a long gap. Yeah. Let me reset the timer. Yeah, started. Given an integer n, in vertices 0 to n minus 1, edges here, bi edges, number of complete connected components of the graph. A connected component is subgraph of graph which there exists a path between any two vertices and no vertices of the subgraph. It's vertices. Okay. So we are given an edges, we need to find the number of connected components, complete connected components. 1, 2, 3. Okay, yeah. 0 to 1 we go, 1 to 2 we go, 2 to 0 we go. There is a cycle. That's fine. If there is a cycle, we skip. Sorry, there are some background noises going on. 0 to 1 to 2 to 0 cycle. What if there is 0 to 5 connection? 0 1 0 5 1 2 2 0. Why can't we do in degree, right? If the number of in degree values, the complete connecting what is 0 1 2 3 1 2 is a complete since edge between two vertices on the complete since. Okay, so if it first form a cycle to make it complete. I still could not understand what does complete mean here. Complete if there exists a edge between every pair of its vertices. Oh, sure, got it. If there is an edge between every pair of its vertices. 1 2 2 it's there, 0 to 1. Hmm. We find integers and we do BFS or DFS and we check uh, 0 to 1 1 2 2 2 2 0 0 to 1 must be 1 to 2 is there, 2 to 0. I'm thinking if there are 4 vertices, how does the complete graph looks like? 0 to 4 should be there, 0 to 5 should be there, 0 to 6 should be there, 7 should be there, 0 to 8 should be there. Odd degree should be the odd degree of 0 must be the number of nodes. That's what I could understand to be a complete thing. But does odd degree make it complete? No. 1, 2, why? What if 3, 4 are not connected? It doesn't make sense. I mean, they should have given a better example. 0 to 1, 0 to 2, every pair of its vertices. What does every pair? Suppose I have one more vertices 3 here. 0 to 3 must be there, 1 to 3 must be there, 2 to 3 must be there. That's what it means. Oh, makes sense. Degree 1 to 0 is there, 1 to 2 is there, 1 to 3 is there. Okay, our degree of every node must be number of connected components, else but how do you know number of let me think. One thing I understood is more like complete every edge. Suppose if a connected component has A, B, C, D, E, F edges, every pair must have a edge A, B, A, C, A, E, A, D, A, F, and B, B, A, B, C, B, D, B, B, F, C, A, C, D, C, A, C, F, D, A, D, B, D, C, D, E, D, F. EF. So in degree, it's an undirected edge, right? So how does in degree help us? Doesn't even make sense, but hmm. If multiple nodes has same array, then they will become a connected component. What if there is one element which is not having same array? Suppose here we are having 0, 1, 2. Till 0 to 1 we have same array. 1 is connected to something 4. 2 is connected to something 4. 2 will be having a different array. So do we call 0, 1, 2 as a complete connect? No, because which there exists a part between no vertex of subgraph shares an edge with, yeah, we can't say that. If you are considering 0, 1, then every vertex they connect must be having same in degree, else we don't consider it. What's the right way? Let me think in a... First, let me look at constraints, right? It's n star and minus 1 by 2. So, it's fine for me. A is not equals to bi. That makes sense. That's not a problem at all. Mm, what are the things we need? First, we do the DFS of all nodes. So we get a connected component. Then we can store all the components we have visited. Like we have 0, 1 and 2 visited. If at all any of the visited element is not having the same length of connections, we think it is not possible. I'm right. Yeah. This makes sense for me. Any better way? I'm thinking if we use DFS, it works because we are having often place to check. We have often again. Don't know, like I'm thinking why do event drivers for something. Hmm. Hmm. Here we only need to suppose A is connected to B, C and F. The only thing we need to ensure is B, C, F has same number of elements. That's it, right? Then let me think. Can do have multiple maps for it. If we first we'll insert in one map, adjacency map, and then we take another map to check the count of every element in that map. So it would be around n square log n. Does this work? N square log n for 50 square log 50. Fine, it makes sense. uh, yeah, it works. If you want to do better, I think we need to do union. Then what would be the scenario if we do union? Mm, 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 mm. Basically, we need to find uh, wait, let me think. We got rank of both. Mm, 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 mm. Oh, we should also store the number of edges along with rank. So, when edges will become n into n minus 1 by 2, then it is a complete. Got it. So, yeah, it's a simple TSO. Let me explain. First, we check connected components. What we by rank. Now, if we need to do it complete, we need to have an edges count where like edges of that node is equals to let uh, kr components in that k star k minus 1 by 2. Then this makes sense, right? Yeah, it makes sense. What would be the complexity of it? For uh, to check connector components, it's so often, and to check if the edges are doing good or okay, and what would be the space in this case? It's a normal parent, and so not to worry about space at all. Yeah, I think it makes sense. Let's try DSU here. So generic DSU code, we need parent and parent, we need size array, we need edges. Yeah, now we need a void find. uh, oh, we need to return something, we can't do void int x. We need void union. We send nodes into and into v. Okay, here if parent of x is not equals to x, we need to create a new node. Parent of x will become why am I writing a shit code? Next, we need to create a new node for parent of x. Yes, this makes sense. And we just return parent of x. In union, first find out parent for u and v. Okay, if both are equal, then we got edge we just return. Oh, I'm sucking in the syntax today. Now what do we need to consider? Now parent will become u, and we need to connect u and v, so size will increase. Same with the edges. Yeah, this makes sense. Now let's write the code. First we resize it to n. We got n, yeah. Now first size we have 1 by init, and I just will assign a 0 by init and comma 0. Yeah. Now first we need to set parent for every node. For int I equals to 0, I less than n, I plus plus, parent of I is I. Yeah, we got parent. Now we need to set all this, and I plus plus if parent of I is I, then we need to check if it is complete. Int m is like suppose of size of I, yeah. Now if m is equals to no, sorry, not m star m minus 1 by 2 equals to edges of ith node, then we got one possible edge. Yeah, it makes sense, right? Let me take int result is 0 and return the result. Let me run this code once. Size edges and parent. Let me change this. Void union must be definitive. Oh, we haven't assigned it right. For every edges we need to do union. Percentage union of edges. Is this vector or parent? Vector, okay. 0 e of 1. Auto in edges, we are declaring it. So why this e is different? I think it's naming issue. Let's make it onion instead of union. image size of 5. Why image a lambda capture? Just wondering. Expected variable name or this in lambda capture list. What does this mean? Where does this issue come from? It's fine to assign it, right? Capture list. This is because of this need. Let me think. I find this is fine. This is generic, but here expected variable name or this in lambda capture list. Issue is not here. Let me go through it once. There is the issue. We are having parent size and edges. Will initially have 0, 1, 2, 3 as parent, size as 1, 1, 1. Makes sense. When we go through every edge and we'll assign union of it and we'll merge them. Here, we find the parent and now we merge them. If for the same, we just add the edge and okay, this makes sense. Oh wait, can we merge them? Oh, got it. AI and PI are not in the order. If U is greater than V, let's swap of values. comma v. Oh, not u equals to v. We need to check size, right? Size of u less than size of v. Yeah, this makes sense. Still, we're getting issue. Is this because of this? What is the issue? Why is this an issue? Size of I. Why? What is the issue here? Why am I getting compiling error? Vim is not at all initialized anywhere else. Name size. Let me change the name and see. Sorry. I said replace done. Let me submit now. The same issue comes, I think, issue in the logic. Oh my god. What is the issue? I think this is fine here. Maybe issue over here. Oh fuck. Parent of you is you, not we. But still the issue. Why it is still issue? Oh shit. I was looking for something else. Yeah. Anyways, we found the right issue too. Yeah, we got it. Let me explain on a higher level how things work. So we are having two challenges. One thing, we need to get a connected component in which there is no connect for every connected graph we take it as connected component. We can't take any subgraph of the connected component. This is what they're saying, and we need to check if the component is complete or not. When does the component feels complete? Like every edge has every pair in that connected component has edge. That means number of edges in the connected component must be the number of components into k star minus 1 by 2. This is like a normal thing. Now to check that, why we are using DSU helps in connecting the components. So first we go through each edge and we assign the parent of the edge as the index, and then initially all the edges has the size 1, which is the edge itself. Sorry, all the nodes has the size 1, and initially we put edges as 0. Now we'll process every edge. So now, yeah, we've checked components u and v. If u and v are in different components, we add their node counts together, and we add the edge counts together, and later we add one for the new edge. This is if we are having a different components. Now if they are in same components, we don't need to merge them. We just need to increment the edge count by 1. I hope you got this. Now once we are having a connected component, we need to check if it is complete or not. Now suppose if a component has m nodes and a complete graph with m nodes must be having exactly m into m minus 1 by 2 edges. So now we check whether the edges of I is equals to the required number of edges. If yes, we increment the result because we got one connected component. So in this way, we are using DSA to group to a connected component, and we check whether it is complete or not. The complexity of it is O of n for the DSU and O of k to check if it is connected complete component or not. Yeah, it works for these constraints. Thanks. See you.